Okay, thanks for the introduction. Yeah. Thanks for the introduction. Then I will right away start with some AI-generated images. So, virtual and augmented reality is a rapidly growing market with applications not only in gaming and cinematic presentations, but also in broadcast, music production, social media, healthcare, and education. And spatial audio is hereby the underlying essential technology being used in order to enhance realism by making the environments feel more intuitive and plausible. And consequently, this marks quite an exciting time for audio professionals since VR and AR become the leading use cases for technologies such as binaural audio, object-based sound, and ambisonics. But to fully grasp how these immersive audio technologies function and how they perceive such a convincing spatial realism, it's important to understand the fundamentals. And that's why this talk will give a bit of a review on current binaural technologies as well as the research around it. And for this, I'll cover some theory on spatial auditory modeling, then shift the main focus onto the measurement and rendering of spatial room impulse responses, and then give a little short practical background on the topic of virtualizing multi-channel audio studios. So let's start with the spatial auditory modeling. When a sound is emitted in space, it arrives at the eardrums after a complex series of acoustic transformations. And those are usually shaped by the physical characteristics of the room, as well as the listener. And those of the listener are usually referred to as head-related transfer functions. And those are caused by the individual head, torso, and pinna morphologies of the listener. And their time domain equivalent is the HRER, which we can see in the upper plot. So this occurs independently for each ear, resulting in two slightly different versions of the same sound, and provides us with what we call psychoacoustic cues. And these cues are crucial in terms of spatial hearing, since our brain interprets them in order to infer the spatial characteristics and localization of a sound source. And the most prominent binaural cues are the interaural time and level differences, which basically refer to small differences in the arrival time and the sound pressure level that arrives at the ear. And yeah, there's also the interaural cross correlation, which defines the degree of correlation between these signals. So besides these binaural cues, our auditory system also relies on monaural cues, spectral monaural cues, which are basically essential for the vertical localization and therefore sound sources that are elevated. And what we can usually observe is that we have these notch filters which are moving through the spectrum depending on the source elevation. And here we can see that for a 0 degree and a 30-degree elevation. And for our applications now, the question comes up, how can we create a perceptually convincing simulation of these phenomena? And the most straightforward way to do so is to accurately capture or recreate the two ear signals, since those contain all the relevant information that our spatial auditory system needs. And a typical binaural rendering pipeline would therefore look as depicted here. We do have a measurement device, or we measure the impulse responses for a certain head orientation, and then we convolve an unechoic audio signal with that head orientation in order to reconstruct that auditory scene. And in real-time systems, this usually happens in a partitioned manner, so we convolve each block and then, yeah, have a representation. And in practice, we usually also use compensation filters in order to flatten the impulse responses, the frequency responses of the playback and measurement system. And the quality and immersion of these environments then typically strongly depend on their adaptability to dynamic head orientations and position shifts of the listener. And therefore, these environments, the color is missing. Therefore, these environments are usually equipped with motion tracking in order to update the selected impulse response in real time. And in practice, instead of doing that abruptly, which would come with artifacts, we usually crossfade between the blocks. So the core problem hereby, besides the computational effort and the latency, can be seen in the spatial resolution that we require in order to have an artifact-free sampling. And for this, the minimum spatial resolution for head orientations is usually 1 degree, and for translations, so movements across the space, we have a centimeter. And that already shows that the measurement efforts here can become quite enormous and time-consuming if we want to measure all of these. Full spherical HRTF set, for example, would consist of 50,000 measurement points, I think, and we can already imagine that that's not so much fun to measure. And this is how it would look like in practice. We have a dummy head or a person sitting in an anechoic or reverberation-free room, and then put these little in-ear microphones into the ears in order to measure the transfer functions. Yeah. So now the question could come up, why not just use the data sets that are available? There's enough HRTF data that we can just employ. But in practice, it has shown that individualized transfer functions strongly outperform non-individualized ones in terms of perceptual quality. So non-individualized HRTFs hereby, for example, have a very poor externalization, which means that we localize sources in head rather than out of head. And on the other hand, they deliver poor localization. And that usually comes with ambiguities in terms of front-back or top-down reversals. And if we, for example, try to pan an audio source around the head of the listener, and it just ends up being panning from the left to the right with some weird fluttering effects, that's usually due to mismatching spectral cues. Individualized ones, on the other hand, bring quite an increased localization, which usually gets to the real sound source localization. And in ideal cases, they even show to be indistinguishable from real sound sources if we put them in a direct comparison with real sound sources, as long as we have the visual cues. And now for sound sources to coexist next to real ones, as we would, for example, desire it in AR applications, this depicts quite a promising and essential aspect. And this is for industry as well as art applications likewise. And the market here also shows some improvements in open-ear consumer headphones, which are aiming to minimize the occlusion effects in order to have no coloration effects on the sound sources that are existing in the real world. And again, this can be quite promising for mixed reality applications. So to address these challenges in research, there have been quite some approaches in order to develop more elaborated techniques. And these, for example, include the matching of features in order to pick head-related transfer functions from a database, which basically means that we would choose ears that are most likely resembling the results from our own ones. And there are different approaches with different aims. On the other hand, we could simulate them based on 3D scans, for example, or we can just synthesize them by measuring a few head orientations and then, for example, interpolate between those, or extrapolate, which basically means that we take 2 reference points and either compute a mean inside or we expand the scale. And as in most fields, also here machine learning is coming more on the uprise, and most recently also we can generatively generate these HRTFs. But yeah, still we see it's quite an effort, takes some time to get into that, and then the question comes back, why not just use data that's already existing? And even though non-individualized transfer functions are maybe not optimal, they can still deliver quite sufficiently realistic auralizations that are partly hard to distinguish from real sound sources if we don't put them in a direct comparison to the real sound sources. And yeah, some of this research also showed recently that we can actually relearn psychoacoustic cues if we use a certain set of HRTFs, which we get used to at some point. Yeah, so far that has covered only the direct sound source, the way from the sound source to the listener's ear, basically in a free field condition. But of course, real acoustic environments are much more complex than this. We have room acoustics, we have reflections from the ceiling and the walls and some objects. And all of these contribute to our spatial impression and the perception within a certain room. And therefore, for XR applications, or generally these applications, it becomes way more interesting, of course, to recreate also these room acoustical properties. And while most VR applications usually do that with highly optimized solutions, usually room acoustical simulations such as ray tracing or portals, they require quite an intensive input. So we need to reconstruct our room, we need to set the walls, we need to have all these input data ready. And they also just offer a limitation because we need to approximate a lot of things. We cannot have a detailed reconstruction of the most rooms. And therefore, measurements often allow us to reconstruct way more complex scenarios without the effort of virtually recreating them. If we think about the AI example from the beginning, then we could imagine that we need to put all of these room acoustical properties like the sofa and everything into a virtual model in order to get the room acoustics. And if we take a look at our pipeline from before, then this can be achieved by placing a dummy head into the center of a room and then measuring the binaural room impulse responses with it. This usually captures the psychoacoustic cues for the entire room. But again, we have to do that for specific head orientation. And here we again end up at the point that if we have to aim on a dynamic scenario, then we need to measure all the individual points for each of the head orientations. And again, this might not be so much fun, especially now we need to do it for every room that we try to recreate. And at this point, an alternative is to measure the entire sound field. To measure the entire sound field with a microphone array in order to capture the directional components and all of this individual parts of it. And those measurements, therefore, not only enable a faster measurement, but they enable that we can render the signals even using individual head-related transfer functions. So in case we have some of those already measured once, then we can just employ them with microphone data. And while this covers more the binaural reproduction in this talk, it is to mention that these can also be used in order to be played back on microphone loudspeaker arrays. Yeah. To start with, there are several types of microphone arrays. We do have B-format microphones with 4 capsules at the faces of a tetrahedron. Then we have higher order microphone arrays which facilitate sound field decomposition and manipulation. Then there are perceptually motivated configurations that are by design carefully configured in order to capture useful signals perceptually. But we can also think of rather arbitrary or head-worn microphone array shapes, as it's usually given with head-mounted displays. And besides these distinct array types, there are several processing techniques which define the core of the binaural rendering. And those I'm going to talk about now. This is the binaural rendering of ambisonic signals, then beamforming-based approaches, parametric approaches, perceptually motivated methods, or the use, again, of machine and deep learning. Yeah. So the one that is most familiar, I guess, is the ambisonics rendering, and for that I'm taking a short detour through the ambisonics theory. And yeah, ambisonics is basically a sound scene codification format that we can use in order to decompose our sound field in spherical basis functions, which are depicted here. So we have these SH basis functions, And as we can see from the visualization, the mathematical functions describe the patterns across a sphere or a spherical surface with an increasing resolution. Here, if we go up to the higher order. So, in terms of microphone arrays, this means we require spherical shapes in order to decompose them into these SH domain basis functions, while the number of microphones hereby directly correlates with the ambisonics order n. And here's the key connection. When we consider an HRER measurement, then we are basically sampling points around the head of a listener, and those we can therefore map onto a sphere, and consequently we can derive the spherical harmonics basis functions from here. And this doesn't only hold for impulse responses, but we can also use it for whatever signal we run through. And this transformation hereby offers two main advantages. On the one hand, it's quite flexible in terms of rotation. And on the other hand, the sound field facilitates decomposition strategies and advanced processing, as for instance, beamforming techniques. And the directional selectivity and the shape of these beams is then usually depending on the ambisonics order. And here we can see some of these shapes. So based on that theory, we can now go into the binaural reproduction of these signals. The first one hereby is the ambisonics methods. And what we basically do is we obtain the spherical harmonics representation of our sound field, measured with a microphone, as well as the representation of our HRTFs. And then we merge them in that domain in order to obtain our two binaural signals. This is computationally very efficient and facilitates manipulation, since we inherently separate the sound field from the head-related component. But it comes at some limitations. On the one hand, the spherical microphone area order defines the spatial resolution, and this comes due to order truncation, which means that the lower order representation of our microphone, which is limited by physical capsules, dictates the threshold from which on we have to truncate the higher order representations. And besides this, we have spatial aliasing, which is similar as time aliasing, just in the three-dimensional domain. Yeah. And as we had it before, they are fairly simple or facilitating rotation, but translations or movements within that sound field are not quite trivial, which is a downside. And on the other hand, spherical microphone arrays are required for these processes, but as we remember the head-mounted display, then we know that they are not built into these consumer devices usually. And at that point, we come to rather beamforming-based methods. So this merging, which I just described for the SH domain, we can also do it in the time domain, which means that we basically decompose the sound field back into a discrete representation of plane waves, and those we then filter with our impulse responses, directional impulse responses. So simply said, we spatially filter our sound field in order to get a directional component, and this component we then simply treat as a virtual source, and therefore we can use it with our directional filters. And this is especially beneficial in terms of non-spherical array shapes. So if we think about some applications like teleconferencing or a virtual theater or these kind of things, or we go back to our AR example from the beginning, sitting in the living room, having one of these glasses on top, that's usually facilitated when we apply beamforming-based methods. And another family that I'm not going into by too much depth, but which most of you or some of you eventually know from the Sparta plugin suite, are parametric methods. And if we think about the ACS talk from before, then we can still remember that there are these consecutive regions in time, which is the direct sound, the early reflections, and the late reverb. And these parametric methods basically initially separate these consecutive regions. So we have a direct sound that is routed into a different pipeline as our diffuse kind of part. And for the directional components, we basically then estimate a sound field and estimate some parameters, like the direction of arrival of a sound source. And those we can then, just like before, filter with our directional components. So we have a directional component filtered with our HRTF, and then we have a physical reconstruction of the source there. And the diffuse part, on the other hand, is just routed through all of these HRTFs individually to distribute them. And why I'm bringing this up especially is because they're perceptually very good for low order recordings. So if you have a low order first order recording, and it seems still always blurry if you decode it to binaural, it might make sense to eventually just apply some of these techniques, which is doable with the Sparta plugin suite. There are some approaches that leverage the quality. And I'm again seeing there's no color on these plots. On my computer, it all looks a bit more colorful. So another approach for the positioning of these microphones within an array is could follow rather perceptually motivated configurations, which means these configurations could preserve the psychoacoustic cues that we talked about in the beginning. And hereby the discrete signals of the microphones are just directly routed into the directional filters, and there's no prior decoding or encoding required. The spacing and the relative angles of these microphones could then, for example, define these parameters here, which are the interchannel time and level differences, as well as the interchannel correlation. And for those who still have in mind the first slides, here it might ring a bell because there we talked about the ITDs and the ILDs, which are equivalents here. So these then define the spatial image. The ICTD and the ICID ratio, for example, they would define the trade-off between the spaciousness and the localizability of a presented sound, as well as the depth and the spread of sound source. The ICC, on the other hand, defines the source width or the perceived listener envelopment, which means we are being surrounded by sound. And if we play them back on a physical loudspeaker array, then the ICC would also define the size of the listening area that we at the end can cover with it. So again, they deliver a perceptually quite convincing result, even with a small number of microphones. One of the downsides, though, is that they don't have a generic representation of the sound field, as we had it before with ambisonics, although there are some recent approaches that also manage to bring those into the intermediate state. And additionally, they require highly specific array configurations. And this is how some of those could look like. This is from the applied psychoacoustics lab, which I think you don't see because of the table. But it's basically array configurations that are defining how the spacing and the positioning and the polar patterns of microphones should look like in order to achieve these perceptual results. And a detailed description is also available on the website, so I can recommend to check these out. Also from there, and a few other people, is the Echo Library, which is basically a collaborative research project on 3D microphone array techniques for orchestral recordings. And it's a database almost of 50 gigabytes of recordings that can be used to teach or just to experiment a little bit. So the last one, again, machine learning techniques, they are up on the rise. And And neural networks also here find their way throughout various processing stages of the signal processing of these microphone arrays. And just to cover a few, these deep neural networks are increasingly employed for scene classification or event detection or source separation, as for instance with ambisonic signals, we know it's always collapsed into a scene, and also the spatial upsampling. And in general, one can say that these methods hold the potential to overcome the limitations that we are given due to the physical constraints of microphones, or just generally the microphone data that we have. Yeah, and that was quite a bite of theory, I think. So I'll zoom out a little bit and shift it to the last part. So one trend in spatial audio is a reproduction of multi-channel systems in the binaural domain. And while multi-channel setups are getting more and more used in home setups, as for instance, the couch where we want to have a Netflix or a Schlagerparade in spatial, the studios in which we create this content still remain a tight resource. So, yeah. But if we here think about the perceptual difference of rendering a higher order ambisonics file binaurally to playing back that file on a 7.4 system, then we see that it might need this intermediate state in order to binauralize these spatial works. And the auralization can hereby be achieved either with a measurement or a simulation. And yeah, and that we do in the room in which our multi-channel setup is placed. So most simple, we just take a dummy head or put ourselves into the center of our loudspeaker array, put ourselves in-ear microphones in the ears, and then we measure impulse responses from that system. And alternatively, as we just heard, we can also just put a microphone array if we have one available, and then capture the entire sound field. And this we usually iterate over all of the loudspeakers, and then we obtain a convolution matrix, which we just route the loudspeaker signals into in order to obtain a binaural playback. And these matrix convolver are, for example, available with the MCFX plugin here, as well as the matrix convolver from the Sparta plugin suite. And there's also a very freshly bounced PD external for PD fans from the IEM, which is part of the IEM matrix package. If we have spherical microphone array data, then we can first convert those arrays to the spherical harmonics presentation as we had it before, and then use binauralizer in order to convert these ambisonic signals to binaural. Yeah. At SIMT, we also have one of this with a little bit less flexibility. It's a simple binaural decoder of the sound system here. And the BAERs are measured with a dummy head at the room center location of each loudspeaker, and then simply embedded into the VST or standalone as binary code, which means that artists can just simply put this past their decoding stage and therefore virtualize their composition remotely. And for those, that means that the production that they have planned can actually start before they actually visit their location. And usually that helps to bridge the gap of considering spatialization more as a post-processing step and try to actually compose for a certain room. And usually time is a tight resource, and that's something practical here. So as a venue that is hosting artists, it might actually be a consideration to just measure impulse responses from the loudspeaker system and provide those to the artists because it helps them to stretch their time on site. Yeah. And when we shift the focus on simulation, then we have a few other examples or plugins that provide additional control over the room acoustics, as for instance, expanding the reverberation time, and therefore ideally to match the simulation with the actual target room. And this could look like this. As with the Virtuoso plugin, again, this is from the Applied Psychoacoustics lab. Yeah, and here we can even employ individualized HRERs and therefore get a better perceptual result. But there are also some other solutions, such as DVR or the Fraunhofer MPEG. There's a Dolby Atmos version of this, Novonodes and some others, and especially the Eclipsa audio renderer is to mention here, since it was just published as open source, and yeah, that's quite a rich library. And that's it so far from my side.